Hello all, I welcome you to the final week of this particular course. So today we'll recap the stock market prediction problem that was motivated as part of the sequential learning paradigm in the last week, and in today's lecture we'll try to answer the first of the two questions that the professor had posed in the last week, namely how many mistakes can the algorithm make in the worst case, or rather what is a bound or the maximum possible number of mistakes that the algorithm can make before it finds the single stock market guru or a small set of consistent experts. So we look at that today. So I'll briefly recap the stock market problem just for completeness sake. So okay, so we have the problem, and in the problem we first we receive some advice from a set of experts, say D experts. In our example it was 100. So, and once we get the advice, we need to make some algorithm, or in our case ourselves, we somehow input this set of advice and make a decision using that on whether we want to invest or not. This advice is of two types, is either yes or no, and we have D such inputs, and our algorithm somehow makes a decision upon its final action on whether we will invest in the stock market or not for that particular day. So somehow use advice, which is what the algorithm is doing. Algorithm and make a decision. Okay, super. Now we've made a decision, and this is where the learning part comes. So we make a decision. We suppose decision was no, so we don't invest in the stock market. But it so happens that the market actually went up. So the environment or the stock market will return a feedback saying yes, and we see that we said no, so our algorithm has made a mistake, and so on. So here we later use that particular feedback to later tune or learn from that. The algorithm somehow learns from that. So that is so receive feedback from the environment, which is the market, and somehow learn from it. Alright, so this was our setup, and following these 3 points in the previous lecture, we came up with this algorithm called which we'll call the majority algorithm. So this is how the majority algorithm works. Majority algorithm. So the majority algorithm tries to so it keeps it invests based on a majority of consistent experts. This set of consistent experts is maintained or rather is updated after every round, where the set of consistent experts would be a small number of people, or one, which would comprise the guru himself, who were consistent with whatever feedback the stock market was giving. So that we maintain this set of consistent experts, and every round we'll predict with the majority of this particular section of our experts. So what we predict, all of this is from the previous week's lecture. Predict from, okay, so we have this, cool. And now we'll go on with the analysis. So it was a recap till now we'll form. So we want to analyze in the analysis we want to analyze what is the maximum number of mistakes the algorithm can make. We'll also look at the minimum number of mistakes just to get it started with. So suppose we just assume for simplicity, we'll assume there are 100 experts. Now we want based on the previous points, we want our algorithm to make as less mistakes as possible. And one way to do that would be to find the stock market guru, because you know the stock market guru can never go wrong, which is the assumption we make, right? So there exists this one stock market guru who knows, who is guaranteed to give the correct advice, which if you follow, you will never make a mistake. So in order to kind of maximize or minimize the mistakes, the way to proceed about it would be to find your stock market guru and then keep following him after that, and also find the stock market guru in the quickest possible fashion. So we'll have to do that. And in the best case scenario, can you tell me how many mistakes would the algorithm make before finding the stock market guru? So one possible scenario could be this way. So perhaps in the first round itself, one expert saying yes and 99 experts are saying no. So the majority algorithm will take this input, and the majority says no, so it will output no. This goes into the environment. The environment returns a feedback which actually says the stock market went up. So it might return saying yes was a better thing to do, and based on this, the algorithm later kicks these experts who are not consistent with the response of the environment. And in just one mistake, we end up with the set of consistent experts having just one person. So the set of consistent experts has just one person. So that person better be the guru, right? So he's the guru. Great. So this was the best case scenario. You will just have to make one mistake, remove the other 99 people, and so on. There is also, you can also try to think of a scenario where you can make no mistakes and still find the guru, but for that you will have to kind of make sure the tie breaking. So for example, if I do a 50-50, then how you choose which one to select, right? Because when it's 50-50, the group that is the majority is not clear. So once you fix all that, suppose you say 51 people said yes, 51 people said yes and 49 people said no, then I could eliminate the 49, and then I can continue saying 26 and 25, and then eliminate and keep going on until I get the guru without doing a mistake at all, because the majority at that point ends up saying being consistent with the environment's responses. So that is another way, but it's fine. Let's not spend too much on the best case scenario. What we're interested is the worst case scenario, which is what is the maximum number of mistakes that the algorithm can make. So we look at that. Now we saw that the best case scenario was this. So for the worst case scenario, we want to make our algorithm make as much mistakes as possible so that you get the upper bound for it. And the way you can do that is say, let's actually fix a tie breaking mechanism. So if our algorithm ends up with a tie, so if there's 50 people who say yes and 50 people who say no, we'll just say I'll say tie breaking mechanism, if there's a tie, we'll just say always pick yes, some arbitrary mechanism, whichever you choose here wouldn't matter, but yeah, for just to make our analysis simple and to get the upper bound, we'll consider this for now. Okay, so we have this, and now we'll start off, right? So here for the best case scenario, having the majority predict wrong, and not just a majority but a very sizable majority predict wrong, which happen to be in the best case, kind of provides hints towards splitting them evenly, and then making a mistake. So you want to since the objective is to find the stock market guru as quick as possible, in the worst case scenario, we want our algorithm to kick out as less experts as possible in the initial round, right? So in every round we want to minimize the number of experts we are kicking out of the set of consistent experts. In the best case scenario, we wanted to maximize that, so that's why we kicked out all the 99 people. But here we want our algorithm to both make mistakes as well as kick out as less number of people as possible. So then you can see where I'm going with this. So let's actually split our experts into 50-50. 50 people saying yes, 50 people saying no. So this goes to our algorithm, and can you tell me what the algorithm will what decision the algorithm will take, whether to invest in the stock market or not? Well, since here there's a tie and we said in a tie breaking situation we'll always pick yes, so we will invest. So the algorithm says yes, invest. So this goes to my environment, so which is the stock market. The environment returns feedback which says no, you shouldn't have done that. So this is a mistake. So we've made one mistake here. So because of this mistake, my new set of consistent experts will be the set that said no, or they gave an advice no, and this thing goes away. So now, and also observe that the stock market guru is necessarily on the 50 is part of the 50 people who said no in the first round, right? And now we have 50, just 50 experts, at least the set of consistent experts after the first round is 50, and now among this 50, say 25 say yes and 25 say no for the next day, and the algorithm again using the tie breaking mechanism comes up with the decision yes. Okay, so it says yes, but yet indeed again the environment says no, that's a wrong choice, you should have invested, sorry, you should not have invested. So it returns no, and using this decision we can again eliminate these guys, and we have only 25 people who said who were consistent with the environment across the 2 rounds, and we also know the stock market guru is within this 25 members. All right, so this is going on, and you can see both we are trying to make the algorithm make as much mistakes as possible, and we are also kicking out as less number of people as possible, because the majority can never be lesser than 50% in a population. So both of these ideas are respected here, and now can you guess how many mistakes this can make? So it is important to argue why this actually results in the largest mistakes, because let me repeat again, we want the algorithm to make as much mistakes as possible, which would upper bound the total number of mistakes, and you want to kick out as less experts as possible in every round, but this lessness is greater than 50% because the majority is 50% or above, right? So just to drive that point home, if I split a line like this, say this line is a bunch of experts, then this is a majority and this is a minority, and the fraction of this length with respect to the entire length must be greater than 50% for it to be a majority in the first place, which is why we want to kick and kicking as less number of people as possible gives the algorithm an opportunity to make more mistakes before it ends up finding a stock market guru. So we want to find that, and now as we now proceeding with these steps, we see at the start it was 100, then it became 50, then it became 25. So it seems that after every round, in the worst possible scenario, my set of consistent experts reduces by half. So if you do that, then we see if we keep continuing this for a while, then perhaps at some point, say we'll end up with one expert saying yes, one expert saying no, and then the algorithm using the mechanism says yes, the environment says no, just the same repeat as before, because you want to make the algorithm make as much mistakes as possible. So the environment says no, and therefore we eliminate this expert, and we are here, and finally where we end with our consistent set having just one expert in it, and that expert better be the stock market guru. Cool. Now what is this number? So it was 1 at the start, and then 2 here, and so on, and we want to know what this number is, or at least a number that is close to this and higher than that. So we want to bound the number of mistakes, right? So you saw that if I make a sequence in the first round, there were 100 experts, then it became 50, then 25, then say 12.5. Now we'll say if you want to make the majority predict, we want the majority to predict yes, so that so in 25, so I'll just show the 25 case. So for the 25 case, we'll make we want the majority to say yes, so we'll put 13 in yes and 12 in no. Yes, no, and then it turns out that only the 12 people were right, so this becomes 12. Then 12 we'll have them say 6, so that will be 6, and then 3, and now we have 3, so this should have, so I'll just edit this a bit. So the final round would have had 2 people say yes and 1 person say no, and when we do that we'll end up with 1, right? So here we made one mistake which made us go to 50, 2, 3, 4, 5, and the last mistake 6. So we made 6 mistakes. Alright, so now I hope while I was doing this itself, you would have thought about a general formula or a computation that we can do, provided we are given an input, the input D. So we took D as the set of the cardinality of the total number of experts, right, at the beginning. So I hope you come up with it. So what we are doing here is basically, since after every round my set goes down by more than half, so you can see more than or equal to half, so 150, 50, 25, 25 it has gone down a bit more than half, so half is just 12.5, a little more than half if it goes down by, then it is lesser than 12.5, so here we have 12 and so on. And therefore if you want to find the number of mistakes, since there is this exponential decrease by a factor of 2 after every round, we have this. So we basically want to check 100 times half. If we make one mistake, it's 50. If we make 2 mistakes, it's 25, and so on. So how many mistakes should we make to end up with one expert, right? So it's not exact, it need not be exact, but it's some rounding off. How much do we need? So this is, if I simplify this, I have 100 over 2 power x is equal to 1, which yields 2 power x is equal to 100. And if you guys are familiar with the logarithm, then x is simply the logarithm to the base 2 of 100, right? And x is the number of mistakes you will have to make so that the algorithm converges to 1. But since you want to upper bound this, we can just take the ceiling of this to be the answer, because we want x also to be an integer, and what the ceiling basically does is, if I have 1.012, if this is some decimal, right, so some decimal, so this will round it up to the nearest integer, so that would be 2, right? So if I have 0.98, then this would be 1. If I have 0.0012, also this would be 1. So this is the ceiling operation, CEIL, yeah, and this is the notation for that. And so the answer for the number of mistakes is log base 2 of 100. And if right, so now if we compute this value in our calculator, we get so this is equal to 6.64, and the ceiling of that is 7 mistakes, and this is fine. So we just want to end up with a good upper bound, this upper bound which our algorithm can never exceed. It can be equal to it. In the case of 100 it wasn't, but if you say take a pure power of 2, so say 64 or 128 and try it, so this should hold. It should perhaps exactly hold because there's no ceiling to be done because there are no decimals. Here, since it's a 6.64, you have one extra compared to the 6 mistakes we got, but they should hold for all the other ones also. And this tells us some interesting things. So since the number of mistakes is upper bounded by 7, and since it increases logarithmically with the number of experts, if you look at the curve, if you look at the log curve, so this is x, right? This is x, and log x, it's a bit like this. This is 1, and so this is how the log x curve looks like. It's probably not accurate, but yeah, you should perhaps use Desmos and check it. But you can see x increases more rapidly than log x. So log x is a very slowly increasing function, nevertheless increasing, but increases very slowly. And the number of mistakes made by the algorithm being logarithmic to the number of experts indicates that even if you can feel free to increase the number of experts that you're consulting, and that will not really impact the number of mistakes you make in a huge fashion. So it's logarithmic in that sense. It increases slowly, and that is a good point in your algorithm. So if you say I can increase 100 to, I think 128, right? Yeah, if I increase it to 120, I'll still make 7 mistakes. And from 128, if I increase it to 256, then I'll just end up making 8 mistakes, right? So you can see that the increase is drastic with the number of experts, but the number of mistakes you're making is not that drastic, at least the maximum number of mistakes. Obviously, you'll never exceed 8 mistakes, which is based on the way your experts are responding, but 8 mistakes is the upper bound for the algorithm. All right. So we covered in this lecture a small recap of the stock market algorithm. We later performed an analysis of the best case and the worst case of the algorithm, and we concluded that the number of mistakes made by your algorithm, or in the worst case scenario, grows logarithmically with the number of experts that you start off with in the start of the algorithm. Right. So this concludes the lecture for today. Thank you.